Okay, so let's continue on the hypothesis testing, and let's use an example here to fully wrap up these concepts. So suppose we want to test the hypothesis that the average exam scores for girls in our school is only 600 or less. Now, I'm not just picking on girls here. This is the example I got from some of the other sources. It could be boys. You know, girls usually have higher academic scores than boys. So there's nothing to think much about this. It's good though to compare only for girls and boys because indeed there are two distinct distributions. So that's the rationale for thinking of one or another. And so we believe this to be the case because in the past, average of girls' exam scores had been 600 or less. But we're getting some anecdotal evidence suggesting that girl exam scores may be going up. So we may test if this is the case. We'll set up the null hypothesis, which is the standard kind of traditional assumption. So that is that mu, that is the average population of exam scores. Once again, exam score is the variable we're looking into, is 600 points or less. And the alternative hypothesis is that it's greater. So that's how we would set it up. It's really important to lay it out like diagrammatically like this, because this helps us guide the inference and make sure we're being logical. So to do the hypothesis testing, we need some kind of test, a statistical test. And there are many of them, and some of the common ones are t-test or z-test, and you may have heard about these. A z-test is going to be appropriate when we know the population variance or our sample n is greater than 30 instances, 30 individuals. And we can thus assume the sample mean variance approximate the population, because usually the higher the n, the more the sample approximates the population distribution. And also, though, we need to have normally distributed data. So we're already assuming that we have normally distributed data because exam scores follow a normal distribution. And we're going to use the z-test because our sample that in this fictitious example is not greater than 30, but we know the population variance. So we can use the z-test here. The z-test calculates the z-score, that's standard score, and it tells us how many standard deviations. The value we test is away from the assumed population value. If we take a look at it here, we're going to test the z-score. So, and the assumed population values equals 600 or less for the average, but we're testing to see if this comparison here, this test of this value is correct or not. The z-score calculation it's pretty simple. The formula is very simple, but it's a little bit difficult to interpret. And I think generally just notice that it's a difference between the sample mean from the population mean divided or standardized by the standard deviation, which also divided by the square root of the sample size. So it gets a little complex to interpret here, but it's that normalized standardized measure that lets us see how the numbers we're observing fit within the distribution. We'll see more of that here. So one step at a time. So we got the let's assume we have the variance. As I said, the standard deviation, the standard deviation is the square root of the variance of the population of girls' exam scores, and it is 100. So this is the standard deviation, not the average. But we do have the population average as well, and that's why we're going to use the z-test. And then we're going to carry out our study. We're going to sample. Our sample is only 20 because we don't really have much time. We need to, we can only sample 20 people at this time. So we calculate the sample mean. We sample first, of course, and then we calculate the sample mean and sample size of our sample data. And we need 4 pieces of information: the mean score for girls' exams in the sample you obtained, the sample size, which is 20, means 20 girls or 20 exam scores, the population mean, which we already had before, and the standard deviation for the population mean of this variable, which is 100. So we have all the information we need to calculate the z-score. Now, just to note something here, you may say, well, the average, the mean score for the exam is already 641. So that means it's already higher than the population mean, 600. So we can already reject the null hypothesis. But the thing is, because we're dealing with a sample, and we're dealing with distributions of multiple instances, then sometimes the sample that we obtain may be a little bit higher. Maybe there was just a couple people that had, slightly higher exam averages, but it doesn't really reflect the general population of students. So what we want to test is really the statistical inference, and the hypothesis testing lets us know whether or not this value here, 641, is statistically significantly different than the expected population mean by incorporating all this information. So the steps is to add the numbers into the z-score calculation, and we have all the numbers here. It's actually just four separate values: sample mean, population mean divided by standard deviation of the population divided by the square root of the sample. And we get this number over here, 1.8336, which is, remember, the z-score, the standard score is number of standard deviations from the mean. So that's 1.83 standard deviations from the mean. So that value that we got, that's 641, is 1.83 standard deviations from the mean. Actually, that's pretty much what it means, assuming that the mean was 600. But beforehand, to fully complete our hypothesis test, we need to determine the significance or our cutoff point that we are concerned with. And we call this the critical value or significance level or alpha or cutoff point, as I call it. And this is determined by the analysts themselves as part of the study design. So this is something that needs to be discussed. Every domain is different. It's usually 0.05, which means 5% or less of the distribution, because we're talking about distributions, but may change depending on the context. So sometimes it may also be 0.1 or 0.01. And the lower the value, the more difficult it is to reject the null hypothesis. Okay, so the lower the value, the more conservative you're being here with your significance level. And 5% or less means that our values are so far from the mean that it is unlikely that there's only a 5% or less chance that they are drawn from the assumed distribution. And in standard score, 5% of the data is 1.645. We kind of saw that before, but we're dealing with what we call the one tell. Here we have two tells, so 5% is 1.645 z-score significance level cutoff points. It's kind of like right here on the graph. So 0, 1, I guess 1.64% is here. So once again, this is determined by us, the analysts themselves. Maybe we want to be more conservative. We don't want to reject our null hypothesis too easily. So we just move the significance level toward the right. So if we wanted to be even more conservative, maybe we would make it like 1.96. So we want just less, even less than a 5% chance. We want less than a 2.5 or 2.3% chance of that we may assume for our test. So putting everything together, we calculated already the z-score. We saw that was 1.83, and maybe some of you already kind of noticed. So our significance level here is 1.645. So the z-score, let's just focus on the z-score, is 1.83. So 1.83, it's over here. So 1.83 is already beyond the region of the critical value. It's already more standard deviations than we set for our significance level. And the translation for the p-value is just the translation into actually the percentage distribution. So if you just kind of follow along over here, we have 1.8 over here is the percentage of instances. So that's about 97%. Here 97.7, so here's 97%. And you can see here 0.03. The other side of that is 97%. 97, kind of 97.7. So this is not exactly over here. My drawing is not exact, but the p-value is 0.03. And that's the probability that finding this mean, that this new mean is equal to the population mean, which is a very low probability. So in this case, the z-score, it passes the significance value, and it's in this kind of critical region over here. So it's very unlikely that we would get this mean score over here, 641. That's kind of what we are identifying. It's very low chance. And the p-value is, both of these things here are the same, kind of saying the same thing. The z-score is greater than a critical value, or the p-value is less than the critical value or the significance level. So they're kind of opposite, and sometimes might be a little bit confusing, but once you think about it for a while, you get the hang of it. So let's do a kind of last interpretation so we really solidify these ideas here. So the p-value tells us if the value tested, remember we're testing average exam scores. The value tested is so unlikely, so far away from the expected value, that there must be something wrong with the initial assumption. So we're not assuming that, oh, our data is wrong, we sampled wrong, and we need to sample again. No, which could be could be another conclusion as well. If your data is not good, then of course that's another problem. But if you're assuming that your data is correct, that's true, real data that you sampled, and you went random sample and so on, then the p-values tells us that there must be something wrong with the initial assumption if it's so low. So the lower the p-value, the less likely the null hypothesis is correct. In this case, that those values, that those averages were equal. A p-value lower than the significance level means we can reject the null hypothesis in favor of the alternative. So usually low p-value is what we want. Okay, that's what we want. That's what's good. Okay, the lower p-value is supposed to be a thumbs up. We want the lowest p-value, and usually lower than 0.05. Once again, why? Because if you want to reject the null hypothesis, that is, if you want to be statistically significantly, you find statistically significant differences. So once again, our z-score is around over here, 1.8, which is around, which is 1.8, which is very far away from the mean. So the likelihood of getting a mean, a sample mean this far away from the population mean is very unlikely. Therefore, we need to reject the idea that the population mean is, in this case, 600, and accept that we must have a new population mean, and we reject the null hypothesis in favor of the alternative. So we can also do p-values and hypothesis testing for correlations, and in a sense then test for statistical significance. And the null hypothesis in this case would be that the correlation coefficient equals 0, which means no correlation. So we're kind of assuming that two variables, let's say, you know, as we're looking into poverty percent and total taxes of a state, the percent of poverty, people in poverty, and the total tax of a state, it assumes, let's just assume that they are not correlated. That's the null hypothesis. But the alternative hypothesis then would be, no, they are correlated. So the correlation coefficient is equal to 0 in the null hypothesis, or different than 0 in the alternative hypothesis. And so, for example, if we get a kind of low value like this one here, so the correlation coefficient between total taxes and poverty percent was negative 0.06. So that's very close to 0. So it's unclear if this correlation is statistically significant. That is, that this value here is statistically significantly different than 0. Okay. For example, there's another here. Let's talk about poverty estimate. Well, let's say, yeah, poverty estimate, which is the number of people in poverty. This is actually kind of interesting. So you can see that the percentage of people in poverty is positively correlated with the number of people in poverty. So the higher absolute number of people in poverty in a state also means that they have a higher percentage of population in poverty, which is not necessarily the case sometimes, right? Sometimes states that have a higher poverty population may have a lower poverty percent, okay, lower poverty level as a percentage of the population. But the correlation is not very high. It's positive, but it's not very high. So we can test this one here and all of the correlation coefficients to see if this number is statistically significantly different than 0. If it's so far away from 0 that we can assume that we need to kind of reject this null hypothesis and accept that this is a real strong correlation in the broader population. So some of these ideas are fairly complex, and I will going to caution you about using hypothesis testing in your studies. There's some code here if you want to apply, though, for the exercise we had on poverty and income data. And let me just conclude with this caution statement. P-values and hypothesis testing are based on various assumptions about the data being analyzed and the underlying distributions. You can always check if your sample variables follow a normal distribution, and I recommend you to do so, and I might guide you on how to do that. But each model, each test has its own assumptions. So z-test and t-test assume that the variables you're looking into are normal. And so what if they're not? So can you use z-tests and t-tests? No, we can't actually. It's not good. But what kind of tests we use? Well, there are other different tests to use if your data is not normal. But this kind of activity requires a lot of domain knowledge and a lot of statistical knowledge about the assumptions. So not checking or using the appropriate models may generate numbers that look correct. They look like numbers, the functions run, they give you results, but they can be entirely false. So be careful with this work. I highly recommend you look farther, deeper into some of this information. And that's it for this one.